Hello future engineers, welcome to my YouTube channel. If you're still new to my channel, please don't forget to subscribe and press the notification bell so that you will be updated on my future videos. I hope that my videos will be helpful in your studies, especially those who are studying civil engineering. So this is deflection methods 8-in-1 part 3.2. So the first part of the solution to this problem was already uploaded, and I solved the first part by three methods, namely double integration method, area moment theorems, and the conjugate beam method. So in this video, I will solve the same problem, example 3, by the virtual work method, Castigliano's second theorem, and the three moment equations. So here is the third example. Compute theta A, delta A, theta C just to the left, theta C just to the right, and the deflection at C by the virtual work method, the Castigliano's second theorem, and by three moment equations. Take note, the moment of inertia of beam ABC is I, while that of CDEF or CF is 1.5 of I, and the modulus of elasticity E is constant. So by virtual work method, so first for theta A, so we solved for the reactions, and the reactions are just transmitted here. These are the computed reactions from the preceding slides from the previous video. So, or if we are going to review it, then summation moment about C for ABC as a free body equals 0. So reaction at B times 5 equals 25 times 7. Therefore, the reaction here is 25 times 7 divided by 5. So that's why you get 35. So summation versus AY. So the shear just to the left of C should be 10 kilonewtons downward. Then action reaction, so at C right, it should be 10 kilonewtons upward. Summation moment about D equals 0, so reaction at E times 8, then equals 10 times 6 plus 32 times 15 times 1.5. So computing for reaction at E, the reaction at E is 97.5, and you check that the reaction at D is 37.5 by taking summation of moments about E equals 0, then you can prove that it is 372.5. Anyway, this is not important because the sectioning of the beams will be such that we do not consider this reaction. So first for theta A, so we always assume that the rotation is positive or counterclockwise. So I apply the unit couple 1 at A. Then considering ABC, summation moment about C, since this is counterclockwise, the force at B, the reaction at B should be clockwise. So reaction at B times 5 equals 1. So therefore, the reaction here is 1/5 or 0.2 upward. Then summation versus Y at C left, it should also be 0.2. Action reaction 0.2 upward just to the right of C. Then summation moment about D equals 0. So 0.2 times 6 equals upward reaction at E times 8. So that would be equal to 0.15 at reaction at E if you consider CDE and you sum up moments about D. So then for the sectioning, so that's first section, then B to C, then C to D, then F to E, E to D. So there will be 5 segments. Same sectioning as for the original beam. So remember that the virtual work expression is 1 times or EI times quantity 1 times theta A is equal to integral of moment at a section AB due to the actual loads Then moment at the same section AB due to the virtual load. Dx over dx, because we multiply everything by EI for the left side. So EI 1 times theta A equals integral. The moment in this section is negative 25 times x. Then in this section, because supposedly the positive moment about the section is clockwise, if you start with the left, so this is also negative 1 dx. Then for section 2, it is 35 times x, integral of quantity 35 times x minus 25 times 2 plus x. Then for the beam applied with unit virtual load, it is quantity 0.2 times x, then minus 1. So that's the moment at this section due to virtual load. Then plus in next section, CD, it is equal to, because this is a hinge, so it is only equal to 10 times x minus 32 times x over 2, or 10x minus 16x squared. Then due to the virtual load, it is 0.2 times x. So 0 to 6, 10x minus 16x squared, then 0.2x divided by 1.5, because the moment of inertia of this beam is 1.5, or the moment of inertia is 1.5 of I. Then for the next section, which is F to E, it is 0 because there's no moment in FE due to the unit load. So it is just 0. So plus integral next would be 0 to 8, integral of quantity. So moment at this section due to the actual loads is 97.5 times x. Take notes, at the right end, the positive moment is counterclockwise. So minus 32 times 1 plus x, then the moment arm is 1 plus x over 2. So it should be minus 16 1 plus x squared. Then due to the unit load, the moment at this section, considering forces to the right of it, is 0.15 times x, divided by moment of inertia 1.5 of I, or simply just 1.5. So the value of the integral of the first is equal to 50. The second integral is equal to 250 over 3. The third integral is negative 595.2. And the fourth integral is negative 8576 over 15. So if you have a calculator, FX991 ES or ES plus or FX991 MS, then calculators that can perform integration, then we can apply virtual work method conveniently if we have that. But if our calculator is low-tech, then we have to evaluate the integral individually for each integral, and that makes virtual work method not a method that will be the likes of those who want to solve this by virtual work method, because of its lengthy solution because of this integral part. But if you have a calculator, which is a high-tech calculator that can evaluate the integral, then we can appreciate virtual work method. So adding these values, then theta A can now be computed. It is equal to negative 1033.6 over EI, which is the same as the results in the first part about double integration, area moment theorems, and by conjugate beam method. Next, we draw another beam, same beam, loaded with unit virtual work, unit virtual load at A, which is upward, to make it positive. We assume that the deflection is positive. Then let's compute the reaction here. The reaction here should be downward. So downward reaction times 5 equals 1 times 7. So 7 divided by 5 is 1.4. So 1.4 downward here. Then summation versus y, it should be 0.4 upward just to the left of C. Then by action-reaction, 0.4 downward just to the right of C. Then summation moment about D equals 0. This is counterclockwise, so the reaction at E due to this force should be downward. Then reaction at E times 8 equals 0.4 times 6. So the reaction at E should be 0.3 downward. Then the sectioning is already there. Then we set up EI times 1 times delta A equals, due to the load, we copy negative 25x, then due to the unit virtual load, positive 1x dx for the first term. For the second term, copy this moment equation. Then the moment at this section here is equal to 1 times 2 plus x minus 1.4x. So we copy the moment due to the real loads. Then we just modify the moment due to virtual load, which is 1 times 2 plus x minus 1.4x. For the next section, so it is integral 0 to 6 of 10x minus 16x squared. Then the moment at this section is negative 0.4x. So this is just changed to negative 0.4x, then divided by 1.5. So copy, then negative 0.4x divided by 1.5 dx. Then integral from 0 to 8, because here is 0. So 0 to 8, we copy the original moment due to the actual loads, 97.5x minus 16.1 plus x quantity square. Then for this part, it is positive 0.3x. Place that by positive 0.3x, then divide by 1.5 dx. So evaluating the first integral, it is negative 200 over 3. The second integral is negative 500 over 3. The third integral is 1190.4. The fourth integral is 17152 over 15. Then adding these values, we have delta A equals 2100.533 over EI. This is the same as the deflection calculations before in the first part. Next is we remove these unit loads, or we draw another figure, then we apply a unit positive couple at C just to the left to determine theta C left. Then due to that reaction, considering ABC, summation moment at C equals 0, so the reaction here should be upward. Reaction times 5 equals 1, so this is again 0.2. Then just to the left, 0.2 downward. So 0.2 upward, just to the right of C. Then the reaction at E should be upward so that it is counterclockwise, because the moment of 0.2 about D is clockwise. So 0.2 times 6 divided by 8, that would be 0.15 upward. So EI 1 times theta C equals integral, copy the original moment due to real loads. Then there is no moment here because there's no load, so 0. Then plus, copy this moment equation. Then the moment at this section is 0.2x. So we replace this by 0.2x. Then for the third, so we copy, divided by 1.5. Then we replace this by the same, 0.2x also. So integral 0 to 6, 10x minus 16x squared, 0.2x over 1.5 dx. Then for the last segment, because the moment here is 0, is integral from 0 to 8, 97.5x minus 16, 1 plus x quantity square. Then it is 0.15x, just like this, divided by 1.5. So the integral for those same terms would be the same. So here, this is 0. Then next, this is negative 125 over 3. This should be equal to negative 595.2, and this should be equal to negative 8576 over 15. So combining, theta C just to the left is negative 1208.6 over EI, just like before. Then next is we apply a upward unit load at C. So let's apply the unit load at C, which is, it can be applied at the center of C, or it may be applied just to the right of C. So I suggest it should be applied just to the right of C, so that the reaction here will be 0. Reaction at B would be 0. Then summation moment about D, considering this. So this is also 0, just to the left. Then the unit load is just to the right, or even it is applied at C. So 1 times 6 equals reaction at T, which is upward, times 8. So it is 0.75. So EI1 times delta C is equal to, of course, the first term would be 0. Second integral would also be 0. So we begin with the portion CD. So integral of 10x minus 16x squared. The moment in this section due to the virtual load is 1x divided by 1.5, 0 to 6. Then for the last section, integral 0 to 8. So we copy integral 97.5 times x minus 16 1 plus x squared. Then the moment here is 0.75 times x over 1.5. The value of the first integral is negative 2976. The second is negative 8576 over 3. Combining, so delta C is equal to negative 5834.667 over EI, which is the same as before. And finally, we apply a unit counterclockwise couple just to the right of C to solve for theta C just to the right. So reaction here would be 0, because if we consider only AC, remember this couple is just to the right, so it is not part of the free body diagram. So reaction times 5 equals nothing. So therefore this is 0. Then just to the left, reaction is also 0. Then just to the right, reaction would also be 0 by action-reaction. Then if we sum up moment about D, the reaction at E should be downward. So downward reaction times 8 equals 1. So that means this is 1 over 8 downward. So same sectioning. Then we'll begin with the third section CD, because the first two would be 0. So integral from 0 to 6 of quantity 10x minus 16x squared. Then the moment is negative 1. Negative 1. We replace that by negative 1 because it is counterclockwise. Clockwise, supposedly, the moment should be positive clockwise if the section is at the left. So negative 1, then plus for this last section, integral from 0 to 8 of 97.5x minus 16 quantity 1 plus x squared. Then the moment is negative 18x over 1.5. So the value of the first is equal to 648. The value of the second is equal to 4288 over 9. Then combining, theta C plus equals 1124.444 over EI. So that's it. That's the solution by virtual work method. Method is by Castigliano's second theorem. So it is very same as that of virtual work method. So we apply again a positive couple C at A to compute the rotation at A, or theta at A. So by computing this reaction, we note the reaction before, which was 35. So we'll just concentrate on the effect or contribution of this couple. So it should also be upward due to C, times 5 equals couple. So therefore, the reaction here is 35 plus 1/5 of C, or 0.2 of C. So 35 plus 0.2 of C. Then summation versus Y. So this should be downward 10 plus 0.2 of C. Then by action-reaction, 10 plus 0.2 of C. Then summation moment about D, 0.2 of C times 6. So the reaction here is upward, reaction times 8. So the original reaction here is 97.5 due to the actual load, then plus 0.15 of C. So same sectioning as that of virtual work method. So the formula is E times I times theta C is equal to integral of the moment equation in the section AB here, then times the derivative of that moment equation with respect to the couple. So it would be negative 25 times x minus couple, then the derivative is negative 1 because the derivative of negative 25x minus c is with respect to c is negative 1 dx. Then for the next section, it is equal to integral of quantity 35 plus 0.2 c minus 25 times 2 plus x minus c, which is this. Then the derivative of this moment equation is 0.2 of x minus 1 dx over 1. Then for the third section, it is integral of quantity 10 plus 0.2 c times quantity x minus 16x squared. Then the derivative of 10 plus 0.2 cx minus 16x squared with respect to c is positive 0.2 of x. Divide by 1.5. Then lastly, in this section here, integral of quantity 97.5 plus 0.15 c times x minus 16 times 1 plus x squared. Then the derivative is 0.15x dx over 1.5. So the derivative, before we perform the integration, or prior to performing the integral, we set the value of c, which is only invented, which is 0. So that's 0, 0, 0, 0, 0. Then the value of the remaining integrand, the integral of the remaining expression would be equal to 50. The second one is equal to 250 over 3. The third is negative 595.2. The fourth is negative 8576 over 15. So combining, theta A can now be computed equal to negative 10333.6 over EI. Next, we apply a unit upward load at A. We remove these reactions. So upward load at A, which is P. Then we compute the reaction here. So because the reaction here is 35 due to the actual loads, and it is upward, then it is 35 times 5 plus P times, so due to P, it is 35 times 5 plus P times 7, or minus equals 0. So reaction here is 35 minus 1.4 of P. Then action reaction, summation versus Y here. Then this should be 10 minus 0.4 P. Action reaction 10 minus 0.4 P upward. Then summation moment about D. So due to P, it is negative 0.4 P times 6. Then the reaction here, which is assumed to be upward, equals reaction times 8. So just consider the contribution of P. So it is 97.5 minus 0.3 of P. So again, negative 0.4 P times 6 equals reaction here times 8. So the reaction here, due to, in terms of P, is negative 0.3 P because we assume that it is upward. So by integration, AI delta A is equal to integral 0 to 2. The moment here is Px minus 25x times quantity derivative of Px minus 25x with respect to P is x, then dx over 1 over EI1. Then plus integral in this section here is integral of quantity 35 minus 1.4 P times x, then plus P times 2 plus x minus 25 times 2 plus x. So which is this? Or P minus 25 times 2 plus x. Then the derivative is negative 1.4x, then plus 2 plus x, which is 2 plus x times P. Derivative is 2 plus x with respect to P. Then for the third integral, integral of quantity 10 minus 0.4 P times x minus 16x squared. Then the integral is negative, the differential is negative 0.4 of x, then divide by 1.5 dx. And for the last section, it is integral of 97.5 minus 0.3 p times quantity x, and minus 16 times quantity 1 plus x squared. The derivative is negative 0.3x dx over EI. So before we evaluate the integral, we set the value of p is 0 because it is just invented. Then the first integral is equal to negative 200 over 3. This integral here is negative 500 over 3. This third integral is 1190.4, and the fourth integral is 17152 over 15. So combining these values, delta A is equal to 2100.533 over EI. Then we apply a counterclockwise couple just to the left of C, which is now this. So the reaction here due to C, don't mind the concentrated load because it is already 35 upward. So reaction here is upward, so positive times 5 equals C. So the reaction here is 35 plus C over 5, or 35 plus 0.2 of C. Then the reaction here is 10 plus 0.2 of C. Action reaction 10 plus 0.2 of C. Then here 0.2 of C times 6. This should be upward, positive in terms of C, equals reaction times 8. So 0.2 times 6 divided by 8 is 0.15 of C. So that's why the reaction here is 97.5 plus 0.15 of C. So in the first section, there's no C here, so it's 0. In the second section, let's proceed to the second integral. The first is 0. So EI1 times theta C just to the left equals 0 to 2 of negative 25x times, of course, derivative of negative 25x with respect to couple C is 0. Then plus integral 0 to 5 of 35 plus 0.2 of C times x minus 25 times 2 plus x. Then the derivative is 0.2 of x with respect to C. Then for the third integral of quantity 10 plus 0.2 of C quantity times x minus 16x squared, the derivative is 0.2x divided by 1.5 dx. And the last integral of quantity 97.5 plus 0.15 C of x, then minus 16 1 plus x squared, derivative is 0.15x divided by 1.5 dx. So the value of the first integral is 0. The second one, set the value of C0 first before integrating. So the first is 0. The second is negative 125 over 3. The third is negative 595.2. The fourth integral is negative 8576 over 15. Then combining, theta C left equals negative 1208.6 over EI. Then for the next is we apply a unit upward force at C just to the. So take note that's just to the right. So summation moment about C is 0. So reaction in terms of P, reaction times something equals 0. So this reaction at B here is not a function of P. It is 35. So summation first is Y, so 10, not a function of C. Then we have 10 upward, action reaction. Then summation moment about D equals 0. So P times 6 upward, clockwise equals reaction at E times 8. So 6P divided by 8 is 0.75. So therefore, the reaction at E is upward 97.5 plus 0.75 of P. So the integral of the first section is again 0 because the derivative of the moment equation is 0. So let's proceed. The second also it's 0. So let's proceed to the third because only the third section is a function of P. So integral of quantity P plus 10 times moment arm x, then minus 16x squared. The derivative of this equation is, with respect to P, is x dx over 1.5. Then plus, in the next section, integral of quantity 97.5, 0 to 8 of plus 0.75 of P times x minus 16 times 1 plus x quantity square. the derivative of this moment equation with respect to p is 0.75x dx, and the whole integral divided by 1.5. So set the value of p to 0 before integrating. So the first integral is negative 2976, the second is negative 8576 over 3, then combining delta c is negative 5834.667 over ei, just like before. The next is we apply a unit positive counterclockwise couple at C just to the right. And again, the reaction here is not a function of C because the couple is not involved if you isolate ABC, because the couple is applied just to the right. So that's 35 kilonewtons here, downward 10 kilonewtons, then 10 kilonewtons upward. Then at E, so if we sum up moment about D and we assume upward direction, so due to C, it is negative because reaction times 8 plus couple equals 0. So it is, the reaction here therefore is 97.5 minus C over 8. So that's it. So EI, theta C, so we begin with section CD because the derivative of moment in this section AB and in section BC would be 0. There's no couple function here. There's no C, or the moment is not a function of C. So we start with section CD. So it is equal to 10 minus C, quantity times x, minus 16x squared. Then the derivative with respect to C is negative 1 over 1.5 dx plus integral of quantity 97.5 minus C over 8 quantity times x minus 16 times 1 plus x quantity squared. Derivative is negative x over 8 divided by 1.5 dx. So setting the value of C to 0, then evaluating the integral of the remaining terms, then we have 648 in the first, second 4288 over 9, combining theta C plus is equal to 1124.444 over EI, just like before. So that's it. That's the complete solution by Castigliano second theorem. The solution by three moment equations. So first, we find the moment at B to be negative 25 times 2 or negative 50. So let's put the reactions first. So moment at B is negative 25 times 2, so negative 50 kilonewton meter. The moment at D is 10 times 6 minus 32 times 6 times 3, or 97 times 8 minus, considering the forces to the right, 32 times 9 times 4.5. So either way, the moment at D is negative. So 10 times 6 minus 32 times 6 times 3, negative 516. It is also equal to 97.5 times 8, then minus 32 times 9 times 4.5. It will give you the same answer of negative 516 kilonewton meter. So first, let's have the, by the way, the moment at E is negative 32 times 1 times 0.5, so negative 16. So let's have the three moment equation in CDE to compute delta C. So three moment equation in CDE. Take note that the moment at C is 0 because this is a hinge. Then 0 plus 2 times moment at D, negative 516 times 6 over 1.5 because the moment of inertia is 1.5, plus 8 divided by 1.5 plus moment at E, which is negative 16 times 8 divided by 1.5 plus 6A1A over E1, 6A area 1 A over L1 I1 L1, so it is W32 6 cube over 4, that's the formula, over 6 times 1.5, and W 6A2B over I2L2 is 6 is equal to W32 times 8 cube over 4 divided by 1.5. divide by 1.5. So 0 plus 2 times negative 516 times 6 over 1.5 plus 8 over 1.5. So the next is plus moment at E, which is negative 16 times 8 over 1.5. Then plus 6A1A over I1L1 is 32 6 cubed over 4. Then we divide it further by 1.5 because the moment of inertia is 1.5. That's the reason we divide WL cube over 4 by 1.5. Then for 6A2B over L2I2 is it's also 32 8 cube over 4 times 1.5. 32 8 cube over 4 times 1.5 equals 6EI. So take note that the horizontal line is, the reference is D. So because E is a support, HE is 0, then HC is not, because definitely this hinge here will be either moving downward or upward. So equals 6EI, HC over 6 plus 0, because HE is 0, definitely the horizontal line through D passes through E, while the horizontal line through D, C will be displaced either downward or upward. So that's why there's value for 8 sub C. And computing for 8 sub C, 8 sub C is negative 5834.667 over EI. Negative means point C is below the horizontal reference line at D. So because it is below, then that is also delta C, which is negative. So delta C is negative 5834.667 over EI. So which is the same answer as before. Then we consider A, B, C because we have found delta C. So, but before that, let's do the moment diagram by parts. Let's make B as the moment center. So we have 25 times 2, negative, then 10 times 5 is 50. So moment at B is 50. Then for the portion CD, let's make the moment center at D. Then we have 10 times 6, 60 divided by 1.5 because the moment of inertia is 1.5. So it becomes 40 over EI, while the moment due to the load is 32 times 6 times 3 divided by 1.5. So second degree, it is 32 times 6 times 3 divided by 1.5 is 384 over EI. So this is the portion of the moment diagram that is important in computing the other elements of what is required in this problem. So three moment equation in ABC. Take note that the reference line is through B, and A and C this will not be on the same horizontal line expected. So 0, moment at A is 0 plus 2 times moment at B, which is negative 50. Then span AB is 2 plus span BC is 5. There's no more denominator because the moment of inertia is 1, or EI is just EI. The moment of inertia is just I. Plus moment about C is 0 because that's a hinge. Then plus 6A1A over L1 is 0 also because remember, we consider AB as simply supported and therefore there's no moment in between due to the load. It acts over the support supposedly. Same is true with BC. There's no value for 6A2B over L2. So 0 plus 0 equals 6EI times the quantity HA over 2 plus 8 sub C, which is negative 5834.67 over 5. So in this equation, only HA is the unknown. Solving for HA is equal to 2100.533 over EI. Because HA is positive, it means point A is above the horizontal line through B, and therefore deflection at A is positive. So A is above horizontal through point B, so therefore delta A is positive 200.533 over EI. Now for the slopes, so we draw tangent line at A, then let's evaluate deviation of B relative to A, which is the moment of area between A and B with respect to B. So EI division of B EI division of B relative to A is the moment of this area with respect to B is 1/2 or 0.5 of 2 times 50 over EI, which is negative, times negative 50, then moment arm is 1/3 of 2, so 2/3. So solving for that, it is equal to negative 100 over 3 EI. So that means that if we draw a tangent line, then because delta A is very high compared to deviation of B relative to A, then from the tangent at A, it will be going down, slightly sloping downward. So the slope at A is expected negative. So if this is the elastic curve from B to A, then we draw the tangent at A. Then the tangent at A should be above B because the deviation of B relative to the tangent at A is negative. So this is the tangent, these light blue center lines or dashed lines. Then from the horizontal, the angle that the tangent at A makes with horizontal is theta A. So therefore, because the distance is 2, then tangent theta A is just theta A. So this opposite side is 2 times theta A. And theta A is negative by the nature that it is sloping down to the right. Then this remaining distance is 2 times, the remaining distance is deviation of B relative to A, which is negative. So that's division of A relative to B. And the total vertical distance between A and B is the deflection at A, which is positive 2,100.533 over EI. Therefore, from the figure, based on distance, so delta A equals 2 theta A plus division of B relative to A. But because some of these are negative, so we used absolute value bars. So absolute value of 2 theta A plus absolute value of division of B relative to A equals delta A. Or because theta A is expected negative, 2 theta A is equal to the negative of absolute value of delta A minus the absolute value of division of B relative to A. So again, theta A is negative 1/2 of absolute value of delta A, which is negative of quantity absolute value of delta A is 2,100.533 over EI minus the absolute value of deviation of B relative to A, which is negative 100 over 3 EI. So supposedly this is in absolute value, but because it is positive, so that's why you can just make it positive. So theta A is equal to negative 1033.6 over EI, just like the answer in other methods. Then next, we compute deviation of B relative to the tangent at C left. So we have to consider area between B and C and take moment about B. So it is 0.5 of 5 times negative 50. Then the moment arm from B is 1/3 of 5, so 5/3. So division of B relative to C left is negative 625 over 3 EI. So that means that that point B relative to the tangent at C is below. Point B relative to the tangent at C left is below. So if this is point C, because the deflection at C is downward, then we draw a tangent line to B, then that tangent line should be above B because division of B relative to C is negative. So that means point B is below the reference tangent at C left. So that's the tangent at C left. Then this distance is division of B relative to C, which is negative because it's below. Then remember that the total vertical distance between this point here and the horizontal line is delta C, and we have division of B relative to C. You combine, then vertical divided by divided by horizontal distance 5 is equal to the slope. But we expect the slope at C to be negative because that kind of slope is negative. It is downward to the right. That's negative slope. So therefore, the slope at C left is equal to negative of absolute value of delta C plus absolute value of deviation of B relative to C left divided by 5. So that's it. That's theta C. This is also theta C left. So theta C left is negative 1 over 5 of absolute value of delta C plus absolute value of deviation of B relative to C. So theta C is equal to negative 1208.6 over EI, just like the answer before. Then let's have deviation of D relative to the tangent at C just to the right. EI division of D relative to the tangent at C just to the right. So it is moment of area between C plus and D with respect to D. So we have 1/2 of 6 times 40 over EI, moment arm is 1/3 of 6 to 2. Then minus 1/3 of 6 times 384 over EI, then moment arm is 6 over 4. So EI division of D relative to C, or division of D relative to C plus, is negative 912 over EI. So again, it is negative. It means that point D is below the reference tangent at C to the right. So that's the tangent at C just to the right. And this is the deviation of D relative to C just to the right. And therefore, the slope at C plus is positive because it is inclined up to the right. And it is positive of absolute value of deviation of D relative to C plus absolute value of delta C. So divided by 6. So it is 1/6. It is positive of 1/6. So this is theta C plus. So EI, or theta C plus, is equal to positive 1 over 6 of quantity absolute value of delta C plus absolute value of deviation of D relative to C just to the right. So absolute 1/6 of absolute value of division of D relative to C plus, then plus absolute value of delta C. So solving for theta C just to the right, it is 1124.444 over EI, just like before. So that's it, and I hope you are able to follow the explanation and solution to these problems. And see you on my future videos.